we looked at series types of induction. I guess that's the first typical sort of problem you look at. But the idea of induction can be applied to all sorts of proofs, not just series type. The other main type of proof in extension 1 are these divisibility questions, proving something is divisible. In this case, we're going to prove n times n plus 1 times n plus 2 is divisible by 3. Now, logically it must be true because you got n times n plus 1 times n plus 2. Well, those three numbers are three consecutive numbers. One of those numbers must be divisible by 3, therefore there is a factor of 3. But that's not proving it by induction. How do we prove it by induction? Same idea, first case. Well, first case is going to be n equals 1, so the first three consecutive numbers would be 1, 2, 3. And that's 6. Now in this case, notice I haven't said left-hand side or right-hand side. There is no left-hand side and right-hand side of this. I'm just trying to produce something that is divisible by 3. Well, yeah, 6 is divisible by 3, so it does work. When I sub in 1, it works. My assumption then, I'm going to assume it's true for any value, where k is some positive integer. Well, how do I write this assumption down? I write it down like this, because if it's divisible by 3, it must be true that it's equal to 3 times some integer. So I've written 3p where p is an integer. Now, it doesn't necessarily have to be a positive one, because negative 6 is divisible by 3 as well. So p is just some integer. That's my assumption. I now want to go and prove it true for the next case, k plus 1. So it would be k plus 1 times k plus 2 times k plus 3 is also equal to 3 times some integer. Notice I've changed the letter because it's not going to be the same integer as the one before. So I've called it q. But again, q could be any whole number. Well, let's do our proof. So I'm starting with k plus 1, k plus 2, k plus 3. I've got to work out a way of getting our assumption into that. I'm not going to expand the whole thing out because if you look at the assumption was k times k plus 1 times k plus 2. So if I just expand out the last parenthesis and rewrite that as k times k plus 1 times k plus 2 plus 3 times k plus 1 times k plus 2. And the first term there is my assumption. So I'll substitute in 3p. Because that was our assumption. So 3p by assumption. Now, remember, I'm trying to show this has got a common factor of 3. And we can see quite clearly there's 3 both there. So let's factorise that. My question is, am I left with an integer? P plus k plus 1, k plus 2. Well, yeah, that is going to be an integer. Because p we define to be an integer, and k we define to be an integer. Therefore, k plus 1 is an integer, k plus 2 is an integer. Multiply two integers together, you will have an integer. Add p with this new integer, it's another integer. So yes, it's fair enough to say q ends up being an integer. But notice, I define what q is, and then I make the statement, well, yes, that would belong to the integers. There's my proof. So now we finish the deductive part of the proof. Hence the result's true for k plus 1 if it's true for k. Now we tie it all together. We induce the solution. Well, since I know it's true for n equals 1, then it must be true for all integers by induction. Let's try this one then. 3 to the power of 3n plus 2 to the power of n plus 2 will always be divisible by 5. Let's prove it true for the first case, n equals 1. I get 3 cubed plus 2 cubed, which is 35, and yep, 35 is divisible by 5. So we know our first case, our base case, is correct. Our assumption, well, I'm going to assume then that 3 to the power of 3k plus 2 to the power of k plus 2 is equal to 5 times some integer. So we're going to assume that to be true. We will now attempt to prove that 3 to the power of 3k plus 3 plus 2 to the power of k plus 3 is also equal to 5 times some integer. So how do I get my assumption into this? Can't just substitute straight in. I'm going to have to rearrange my assumption for a substitution. So what I'm going to do is I'm going to rewrite the first term there. And I'm going to rewrite it as 27 times 3 to the power of 3k. 3 cubed, obviously, 27. I'm going to substitute in for 3 to the power of 3k. So this time when I put my reasoning down, I don't simply say by assumption, because my assumption wasn't that. I've rearranged it. I'm saying, well, my assumption means 3 to the power of 3k would be equal to 5p minus 2 to the power of k plus 2. So that's why I can substitute this in for 3 to the power of 3k. Now I've got to play with this, and hopefully we can pull out 5 as a common factor. So 135p minus 27 lots of 2 to the power of k plus 2, but then I've got 2 to the power of k plus 3. Well, 2 to the power of k plus 3 I could rewrite as 2 times 2 to the power of k plus 2. I can now pull these 2 to the power of k plus 2's together. And I've got negative 27 plus 2, negative 25. Excellent. I've now got a common factor of 5. And pull out the common factor of 5. Now I just have to make sure that this is indeed an integer. Well, p is an integer, so 27p is. 2 to the power of k plus 2. Well, k is an integer. Therefore, k plus 2 is. Raise 2 to an integer, but we know it's a positive integer, because that's what we defined k to be. And that will be a whole number. Now, if it was a negative power, it wouldn't be. But we know it's not going to be a negative power, because we define k to be positive. So yeah, that is going to be an integer. So q will end up being 27p minus 5 times 2 to the power of k plus 2. But the more important point is, yeah, we can confidently say that is an integer. So hence it's true for k plus 1 if it's true for k. That's the deduction we've just made. Pull it all together, induce the solution. Since it's true for 1, now it's going to be true for all integers by induction. Let's take this a step further. Let's play with polynomials. Prove x to the power of 2n plus 1 plus a to the power of 2n plus 1 will always be divisible by x plus a. First case, let's make n equal to 1. We end up with x cubed plus a cubed. Well, we have a factorisation for that. We know it's x plus a times x squared minus ax plus a squared. But I guess the important thing is x plus a is a factor. So it's divisible by x plus a. So that's good. First case works. My assumption. I'm going to assume that it's true for n equals k. Now here's where I've got to be careful. Unlike the last divisibility one, I'm not saying it's times some integer. Now it'll be times some polynomial. So I've called it qx, where qx is a polynomial. Prove it true for k plus 1, and I've now called my new polynomial tx. That's what we're trying to prove. Okay, let's do it. Proof. Well, x to the power of 2k plus 3 plus a to the power of 2k plus 3. Again, I've got to try and get my assumption in. So I'm going to use the same sort of idea that I used in the last one, where I'm going to rewrite the x to the power of 2k plus 3 as x squared times x to the power of 2k plus 1. To x to the power of 2k plus 1, I can rewrite as x plus a times qx minus a to the power of 2k plus 1. Notice I've just said by assumption rearrange because I couldn't fit the whole thing in. So I said, oh, by the assumption rearrange, that's where it's come from. We're trying to show x plus a is a factor, so it makes sense to leave that first term with x plus a already as a factor. And let's work on the other two, and hopefully we can show x plus a is a common factor. Well, what have we got in the other two? There's certainly common factors there. We've got a to the powers, haven't we? And actually I've even highlighted what it must be, because I've rewritten the a to the power of 2k plus 3 as a to the 2k plus 1 times a squared. So your common factor there is a to the power of 2k plus 1. But the other factor becomes, because you've got the negative there, x squared minus a squared. But that's the difference of two squares. So that's x minus a, x plus a. We've now got our common factor of x plus a. So pull the x plus a out. What am I left with? Remember, this time I'm not trying to say this is an integer. I simply have to say this is a polynomial. Is that a polynomial? Well, I get a polynomial multiplied by x squared. It's still going to be a polynomial. And I'm subtracting a to the power of 2k plus 1, which is just some number, times x minus a. Well, that is going to be a polynomial. So yeah, it's times tx. Tx would be this particular expression, but yeah, it's a polynomial. That's not a problem. So hence the result is true for k plus 1 if my assumption was okay. If it was true for n equals k. Well, we know it was true for n equals 1, therefore it must be true for all of these integers by induction. Okay, so we'll add in some divisibility ones. for this. But as I say, in extension 1, it's mainly those two that we'll see. Divisibility problems and series problems. In extension 2 is when we then move it on to inequalities, all sorts of other things with induction. And the other thing with extension 1, it tends to always be positive integers. In extension 2 is when we can move on and go, well, let's prove it true for even numbers. Let's prove it true for numbers bigger than 5, things like that.